Okay, good afternoon, everybody. Welcome to the final session of this program. So today is the 10th day since we started, and it has been a very smooth ride so far. All right, so today's session is going to be a continuation of yesterday's. So once again, my name is Ridwan Salahuddin. If you're joining us for the first time, this is Data Science Fundamentals training. So it's organized by an initiative known as Data for All Initiative. Okay, so today, as I said earlier, we'll be building it up on, I'll be building it on what we discussed yesterday. And yesterday's discussion centered around building a logistic regression model, taking everybody through how the thought process from the start of the model development till the point where you start testing the models for various performance or for getting the metrics. So we stopped at the points, I have it here, where we got an accuracy of 86.7. And I beg your pardon, where we got the accuracy of 84.5. This is the accuracy score here. So we computed some other metrics here that we tried to explain yesterday, for which we're going to give further explanation today. Then we also printed the confusion matrix, which is also going to be explained further today. Okay. So today, this is the outline of what we will be discussing. The entire process of training the model and testing it, we are going to put it into a function. The essence of that is, so typically in machine learning, it's very, very unlikely that the first time you build a model, it gives you a satisfactory result. Even if it does, there's always a room for improvement. And you'd want a way to repeatedly test your model without having to run too many cells one after the other and all that. So to save yourself of repeatedly doing a lot of operations, you'd want to put all those operations together in a function. So we're going to write a function for training and testing the model. It's not going to be anything new. It's going to be built on the various operations we did yesterday. So also, we will do more pre-processing as well. So we'll also try to, although not listed, we'll try to put this pre-processing into a function to ease the process too. So I'm not decided yet. We may use the same function for training and processing, or it may be different functions, most likely different. So now we were going to discuss why the model we had yesterday has 84.5% accuracy. So we'll discuss on why the model is bad and why it is especially very bad. Not just bad, it is very bad. So we're going to discuss why it is bad. So then, in discussing why it is bad, we will touch on understanding some of the metrics. So some of the metrics include confusion. Although confusion matrix is not a metric on its own, it basically groups your prediction as compared to the actual outcome. So it tells you, so how many people you predicted, how many of the people you predicted as going to have this disease 10 years from now, how many of them have it? How many of those you predicted as not having it 10 years from now, how many of them have it and how many of them don't have it? So for each of the predictions, for those that are going to have it 10 years from now, how many have it, how many don't? For those that you predict are not going to have it 10 years from now, how many have it and how many don't have it? So we'll make use of the confusion matrix to see that. Then we'll discuss more on precision, recall, and F1 score. And we'll tell you why for different models, different metrics may be preferred. So depending on the particular case you have at hand. Then what can be done to improve the model? Then we're going to do a conclusion. Okay, so since the class is going to be done on the fly, like as we're discussing it, we're going to be showcasing everything. So I've not really done anything beyond what we did yesterday and beyond listing out the outline. And all right, so I want to see where we left it off yesterday. All right, so yesterday we already imported the necessary modules. We read in the data. We viewed the first 5 rows. We viewed the bottom 10 rows. Then we checked for NA values. And yesterday we said, okay, yeah, we also checked for some statistical, we calculated some statistics on it. Then we also did a box plot, which are folded up here. I folded it up. I'm going to fold it up back so it doesn't take too much time. I mean, too much space. Then we also view the proportion of the record that is true, that is positive and negative, or that is yes in the case of 1 and no in the case of 0. Then we replace our null values, NA values, or null values as it's called, with forward and backward fill. Okay, so we didn't really want to stress ourselves too much by saying, okay, let's maybe use the mean, or we can as well easily use the mean or median or any of the other approaches we can. I mean, we've discussed in the past. So instead of having F fill and B fill here, it's just going to be fill now, for instance, fill now, and you're going to pass in maybe, for instance, I'll say data call dot mean. So now I want the mean to be calculated on the columns, like all the records on a row from the start of the row to the end of the row. So the mean for all those records. So I'll say, okay, although there's actually no need for that, since I'm looping through it, I can just say does mean, and it's going to use the mean instead. But since we've chosen to use forward and backward fill, I'll leave it as that. Then afterwards, we checked how many null values we have. Then we split our data into train test. So we use 25% as the split ratio. So test size is 25% of the entire data, while train is 75%. So we checked the shape, and here, this is where we're detaching the target label from the main data frame. So the target label is the 10-year CHD. That's what you're trying to predict. So we have to detach it so you don't pass it into the training. I mean, if that's what we're trying to predict and you're already training with it, it's like you're giving the model expo. So, and in reality, you won't be having the target when you want to predict for actual situations. Okay, so the next was to instantiate a logistic regression model. So we decided to make use of this solver because the default solver, I think the default solver LBFGS here. LBFGS fails to converge. And we said we had a number of options. We could simply change solver, or we could scale our model. So we're going to try the approach of scaling the model today. Okay, so we've not discussed scaling before. So I'm not sure if this class is the right time to introduce it. It's going to be too short because I'll need to show you how the formula is. Although the good thing about most of these models, a lot of things you have to calculate manually has been bundled up as modules, as methods, and all that. So you don't have to worry about how it is done. Just know how to use it. That's what's most important. Yeah, it's okay to know what it does anyway, but how it is implemented, you don't really need to worry too much about it. So we may still stick with this solver instead, because I don't want to introduce scaling in this class. Then we fit the model on our trained data sets and the target. Then we made prediction on the trained data sets that was, test data sets only to get our prediction. Then we use the accuracy method to calculate our accuracy by passing the prediction and the actual target label of the test data set. We got 84.5%. So we try to calculate our recall score, and we have a decent recall score. But if we look at our precision, we say it is very low. Then if you look at the F1 score, it's also equally low. Then we have the confusion matrix. So now effectively, we've revised all we did yesterday. So today, we simply move on by, like I mentioned, we'll create a function. So I'll put it here. Create a function for training. So create a function for training. Now, okay, so it can be easy for everybody to follow. I said I'm not going to do anything new today in terms of this training. It's just going to be me copying what we have done here. We did a split here, although we don't need this train shape and test shape. But anyway, I'm still going to copy it and remove it later on. Then the accuracy and all this, I'm going to copy all of this here, copy cells. Then I'll come here and paste cells above. Now, I did it for easy reference, so I'm going to delete this as I don't need it. So what I'm going to do is I'm going to merge all of these together as a single cell. Merge cell. Okay, so I have to do it one after the other. So merge cell above, merge it above. So I think there's a shortcut for doing it, but I can't quite remember now. So I'll merge all of it. And finally, this. Okay, so I've merged all of this. So just to be sure there's nothing wrong with what we've done so far. So check the train test splits, yes. Then we detached. So let me add some comments. Detach the target label from the data set. So here, instantiate model. fit model, make prediction on test data, compute accuracy, compute recall, compute precision, compute F1 score, and here print confusion matrix. So all these computes, since we have to print them out, so I'm going to add print function. Print. Okay. So there's still, okay, yeah, it's okay, it's okay. Okay, now we said we want to put all these into a simple function. Now let's look through what are the things we may want to change here. For instance, what are the things we may want to change? Okay, let me just assume there is nothing we want to change for now. So I am going to move this down and define my function as usual. Def train model. So I don't have any parameter yet because I've not decided. So I have to indent all these my own step, right? So basically I've created my function. I really don't need it to return anything, so I'm not going to add return since I'm printing out all I need. I'm not going to add return. If I wanted a return, maybe I would say, okay, return the model, but I don't really need any of those. All right, so basically we have created a function to train our model. You can see how it started. We first ran it cell by cell, then we copied all of them together like we did here and we put it in a function. Now, however, what if I want to make some preprocessing to this data, the data we are training on? Maybe I want to preprocess it before passing it here. You know, at this point, we are no longer processing anything. We're just splitting and training and all that. So I may want to change the data I'm passing in. So I can say, okay, let data be a parameter. So is there any other thing I may want to take? Okay, maybe this test size, I may want to change it. So I can pass in test size here, and instead of defaulting it here, I'll just remove it. Since I have test size here, it's going to pick whatever value is passed in here. It's going to be transmitted here, right? So I can also put a default value and say, okay, let my test size be 0.25. I can change it. Okay, so what else may I want to change? Let's look through. So let's say we want to change the proportion of, okay, I've not really mentioned that. So let's leave it at this for now. So we have our function, and I just ran the cell. So we have this function. Now so I've not run the notebook before. So what I'll do is I'll run the notebook from top to bottom. So run all above so it can be ready for okay. We have 24. So it's the 24th run. Now, so let's test our model. Train model. So we pass in the data, which is, I mean, let's inspect it again, data.head. So we still have our data as this. So we pass in the data. So optionally, we can pass in the test size, but it has been defaulted to 0.25. But let's assume we want to change it to 0.2. Something is wrong. So that's the essence of testing. So let's see where the problem is. So it couldn't split the data. Can we consider a valid collection? Oh, I beg your pardon. Yeah. So this should be test size equal to test size. So because this train test split takes a lot of arguments, you can see there are actually, this means the arguments are actually many. You have to go and know what are the arrays it takes and what are the various options. The arrays it takes, it means it can take a lot of, if I want to split multiple data here, I'll just pass maybe data 1, comma data 2, comma data 3, and so on. And these options too are so many. So for this option, you have to pass it as the options equal to the value. So that's what the problem was. So I'll run it again and see it now. Yeah, so we can see we have the results. Now, here we got 84 points. Okay, I think I should add some description. Accuracy, recall, precision, then F1 score, then confusion matrix. Okay, so I don't need this, I'm going to delete it. All right, so we have it better formatted now. Okay, so we have our accuracy, recall, precision, F1 score, and the confusion matrix. So now let's see, our accuracy is 84.19. Our recall is 69. So you will notice that a lot of times these values get changed when you run it again. So if I were to run this again, it's 4.19, take notes, it's going to change. Here we have is 5.6, and every other thing has also changed. So what happens is that there's something called seed, or degree of randomness. So when most of these algorithms, especially train test split. So train test splits, what it does is to ensure that your model does not get used to a particular order. So when it's trying to split it, so you know we can as well split this. I mean, train test split is just taking a portion of the data frame for training and another portion for testing. We can decide to simply say, okay, we have over 4,000 records. So let's just take 1,000, I mean, from 0 to 3,000 as the train data, and 3,001 to 4,000 as the test data. We can do that. However, there's a bias which can result from the way the data is ordered. So in order to avoid that, okay, so let me make it more intuitive now. So let's assume the person that prepared this data may not be like that, but you can get data set like that, where whoever prepared it has arranged it such that maybe after every 3 records that are negative, the 4th one is positive. After every 3 that are negative, the 4th is positive, and so on. So if there's such order in the data, it's quite easy for the algorithm to pick that and learn with it. And once that happens, you will have a model that is not really doing well, because it has learned a pattern and is using that pattern the pattern that is not really informative. You won't be having it in real life situations. So it has learned based on the pattern. So that is not desired, and that's why the data that you're splitting has to be randomized. So basically, when you split it, for instance, in your trained data, you can have data that is, you can have maybe record 317 in the trained data, and record 318 can be in the test data as well. So you can have something like that. So the record 1 can be in the trained data, record 2 can be in the test data, 3 can be in the test, 4 can be in train, and they will just be mixed up randomly. So that randomness is why this value changes. If I want to avoid this change, so there's a NumPy function called random.seed. So you can use it to fix it, but we're not really interested in that here. So you can make your randomness specific. So if I do that, anytime I run this model, I will always get the same output I got the first time I ran it. So, but we're not really after that here, since we're still training on the basic. So it doesn't matter whether what you get is different from what we got the previous time and all that. Okay. Now, what can we do differently? We've not done anything differently today than creating the function. So let's see the second outline, do more preprocessing. So what other preprocessing can we do to this data? So remember, we said yesterday that the null values, the moment you substitute the null values with some other values, we lose information about whether or not that data was originally null. So how about we find a way to retain that information and not lose it? So this brings us to the idea of instead of replacing null values, before we replace the null values, I beg your pardon, we will simply put a condition, put another column that tells you whether the original column was null. Each value in the original column was null or not. So let's see it in practice. Add a column to check if the data in the original column was null. Okay. So let's see data again. Now, which means we have to revert, because remember sometimes it's a good practice to duplicate. So here I'm going to duplicate. I'm going to say, let this be df, and df.head. So, and here I'll say, let this data be a copy of df. A copy of df. So this way I can retain the original data frame. So here now we want to do something differently than we've done already. So we can now say data. Let's call this data 2. So let's also copy the original df. It's df.copy. So let's say data2.head. So let's check the tail as well. So you can see the nouns are still there. All right, so let's take this, for instance. Let's check the tail. So we can see now nouns, right? So remember, if we say is now, we know it's going to create a mask of true and false values. So what if you simply make this another column? And that's what we will be doing. So maybe we now say, let's have another column. Hold on, let me say new call. So then I can print out new call. So this is my new call. I deliberately made use of the tail, the bottom 5, just to illustrate. So when we want to run it, we will be using the entire data frame. So now, if I want to assign this to this same data frame now, so I'll just say, right? So, but I have to change his name. So I can say this is now. Does it make sense to us? Please, I need somebody to respond, or I need everybody to respond. What I'm doing here, what I'm explaining, is it making some sense to everybody? Okay, I got somebody that responded through chat. Others can also respond through chat or by voice.
Yes.
All right, good. So thanks. Now, I'll take this tail off here so we can run it for the entire column, right? So what we just did was create a new column here, right? And it's going to check if this column, if any of the value is na or not. If it is na, it returns yes. If it is not, it returns no or false. So, and I'm assigning it here, but if you also observe, this can be done in one simple move. So instead of first creating this here, I can simply bring this and put it here. So, and I can just say, let's see data.head afterwards. So if you see data.head, let's go to the end. We can see that there's a new column, BP met is now. So, and if you look through it, any value that is false, I mean that is true, then originally was a null value. So how do we do this for every other column that has null values? Remember, we have more columns with null values. Let's see again. Data.isNow.sum. We have many more that have null values. So how do we do all of these? Okay, so I'm going to write a simple loop that will perform this operation. So when you get access to this notebook, you try to understand how the loop is working. So what I'm doing, I'll explain anyway. So I'm looping through each of the columns in the data frame for call in data 2, right? So data 2 is the new data frame we created. So I'll say data 2. So I'm trying to create a new column for each of these columns. So, and I'm trying to give it a name of the original name and add isna to it, underscore isna to the column name. So it's going to simply, this is the column name that it picks from here, and it's going to add isna to it, right? All right, but I don't want it to do it for all the columns. So I'm going to do something here as well, because I don't want, I'm simply doing is I'm running it for all the columns here. So I'm going to say, okay, data2.isna dot sum. Dot isna. So let me, so you can understand what I'm doing. I mean, so I'll advise at this point that there are times when you see a piece of code and you're struggling to understand what it is doing. So a good practice is to try to break the code down. So here now, I decided to separate what I want to do here and show you what is actually happening. So now this, if I want to access this index, I can just say does index, right? And I get this, all the index. So how about if I really want to access the index where this is true, right? Where this value is greater than 0. So if I want to access just this, so this is same as, okay, let me highlight all. So let me do a sum on it first. We see that there are 7 columns there that meet that condition. What if I take the values? We have false, true, false, true, false, true, false, true, and all. Now, this array, this is like a mask as well. What if I access the original columns here? The length here is equal to the length here. That's the number of items here is equal to the number of items here. If I use this to index this, I'm simply going to get, so let me use this to index it. So we can see this is all we have. There might actually be a simpler way, but this is the way I can think of for now. So this might not be the simplest way there is. There are obviously other ways you can do this. So then the approach I've taken here. All right. So this is what I'll put here, because this one has all the columns I want. So I can delete. Okay, I'll leave this. I'll leave this. So when we're reviewing it, we can see it. Now, for each of these, do this, then data2 call dot isna. I mean, data2 call is going to access the column, and isna is going to get true or false values. So because I want to convert true or false value to 1 and 0, so let me show you something. If I have false and I multiply it by 1, it's going to give me 0. If I have true and I multiply it by 1, it's going to give me 1. And that's what we want. So I'll simply multiply what I have here by 1. And at the end of it, let's do data. Welcome back, everybody. Okay, so data2, we'll do data2.head. So let's run it. So let's see now. We have 23 columns up from the original 13 or how many columns? I mean, about 16 that we had initially. So we have 23 now. Now, using these 23 columns, we'll run the model again. So remember, we've created our model. We've created our model as a function, which is train model. So we're going to use this to run the model. So now our data is no longer data, is data 2. So let's run it. There's a problem. Oh. So we've done this, but at the same time, we need to replace the null values. So in this same operation, I mean, each of the columns that we are picking here already has null values based on this check we did here. Based on this check we did here. So each of these have null values in them. So we can simply say data2 call to data2 call dot fill now. Now, what do we want to fill the null values with? Earlier, we filled it with forward and backward fill. Let's do something different. Let's fill it with the mode of the values. So I don't want to use mean, because if you use mean, if a column like age, I mean like sex, male or not, if it has null values, for instance, it's going to use the average. And you know the average of 1 and 0 and 1 and 0s that are not equal in length is going to be, even if they're equal in length, as long as they have 1 and 0s, it's going to be a number between 1 and 0. So we don't want a situation where male is going to be filled with maybe 0.7 or 0 point something. So it's better to use the mode. So I'm going to say data2 call dot mode. So it's going to tell us the mode, the most frequently occurring value in that range, in that column. So let's run it again. So, and now if we run this model, I'm sure, okay, let's check again whether we have null values. Data2 dot is now dot sum. We still have null values. Something did not work fine. Okay, please spare me a few. Can everybody hear me now?
Yes.
Sorry, I lost connection. Okay, so welcome back. All right, so here we're trying to fill the null values, and so this is supposed to have worked, but I'll try to see what the problem is here. So ideally this should work. I'll check. Yeah, so this looks good. So I'm a little surprised. Fill now, data was called was moved. Well, I'm still lost for, so I'm going to try to instead replace with 0 and see whether that is now dot sum. Okay, so I think the problem is from this mode that is being calculated. Okay, so I guess I was supposed to add dot values, but it shouldn't really be a thing. Data to call dot mode dot values. Okay, so it works now. So it worked now. Yeah, it worked. All right, so it's fine now. So to be sure, let's still check data2 dot is now dot sum. So it's all right. All right, so the next is to train the model. So let's see it. Yeah, and here we've trained it again. We got 85.49 accuracy. So let's look at our confusion matrix, or let's just look at our precision before we go to the confusion matrix. Precision is very low at 0.09. F1 score 0.17. Both of them are equally very low. So let's see what does that imply. All right, so before we interpret the implication of that, we will examine this confusion matrix. I gave a little bit of explanation yesterday. We do it further today. So I'll try to be very brief. So time is already fast spent today. Now, so this is how the confusion matrix is structured. On the column axis, you have the predictions you've made or your model has made. But remember, we have the actual values that we're using to compare with the prediction. All right. So the predicted negatives, most times, at least based on the plots from based on the printouts from the model, the first column is usually the predicted negatives. The second column is usually predicted positives. In some illustrations, if you search about it online, this can be swapped. So if you also look at the actuals too, the first is the actual negatives and the second is the actual positives. It can also be swapped. So in this case, predicted negative and actual negative. So 881 were predicted as negative and turned out to be actually negatives. So let's come to this 15. Predicted positives, actual positives. So 15 were predicted as positive. So ignore, I'm not making use of this run. So these were picked some time, like when I was writing, I just picked it and put the values there. So I'm not making use of this. All right, so 15 were predicted as positive, as going to have this illness that we have been discussing about since yesterday. That 10 years from now, they're going to have it. But only, I mean, out of the 15 were predicted and were actually positive. But if you also look at under these predicted positives, we can see another 158 here that were predicted as positive, but they were actually negative. So this is obviously a flaw. So up to 158 people were predicted as going to have this disease down the line, but but all of them did not have it. This 158. In total, the total predicted positive is 158 plus 15. So 158 were wrongly predicted and 15 were correct. By any standard, that is poor, right? But if we decide to make use of this predicted negative as the standard, so let's look at it. 881 plus 6, which is 887, were predicted as negative. And out of them, 881 were actually negative, were correctly predicted. Only 6 times was this wrong. So if your metric is based on this, then you have a fantastic model. Because if you check the accuracy of this, 881 divided by 6, you're going to have over 99% accuracy. If the predicted negative divided by the total actual negative is what you're using to, sorry, if the actual negative divided by the total predicted negative is what you're using to check the model performance, then you're going to have a fantastic model. However, we know in this context, I mean, we're trying to predict whether somebody is going to have cancer, heart disease 10 years down the line. So we're really not after those that we're predicting as not going to have it. I mean, that's not really our concern. Our concern is the people that are going to actually have it. We want to be able to forecast that they will have it so that they can take measures from now to prevent it. So that means we should cast our attention to these predicted positives rather than negatives. So, and if you look at the predicted positives, the prediction is very bad because 158 were wrongly predicted as going to have it, that is eventually have it. However, if we come to the actual positives versus predicted positive. So the actual positive, actually 6 plus 15 people, which is 21 people, actually have the disease down the line, right? But 15 of them were correctly predicted as going to have it. So somehow you may think, okay, maybe this is not bad. This is not bad. And that's why if you look at this recall score, it is this high. But that's because, anyway, I'll say it's still generally okay. I'll say it's still generally okay. It's still generally okay. But as mentioned earlier, the reason I say it's generally okay is not really the best, because out of 21 people, you only got 15 correctly, 72%. It could be better. But the fact that up to 158 people that won't have it, you classify them as going to have it. If this requires them to take maybe medication that is going to have side effects as well, so you would have made this set of people to start taking this medication. So I'm trying to make you see the impact that this can have, especially this particular use case. I mean, other use cases can be interpreted differently, but this particular example, so let me try to give that interpretation that these people that you predicted as going to have this disease, 158 plus 15, you only got 15 of them correctly. So those 15, they know that they're going to have this disease. So even if they have to take those drugs that's going to have side effects, they know the side effects compared to the effect of having this heart disease, they can still manage the side effects. But the person that is actually going to be healthy 10 years down the line, that you've wrongly classified as going to have this disease, you will now force this person to take this drug, and this drug is going to have side effects. So you could have done your job well and correctly predicted this person as not going to have it and save the person of this side effect. So this is the effect of having a bad model. Or let me say the effect of various metrics. So now let me talk more about these different metrics. So for different use cases, different metrics will matter to you. Our goal here, clearly, is more focused on, more importantly now, let me leave out the illustration I gave just before now. So the actual positives here, our goal is to predict people that are going to actually have this disease correctly. So what this means is we want to reduce this cell to the barest minimum, and we want to increase this to be as close as what this total is going to be. So let's see it. You know, if I can reduce this, if this number were to go down, the only place it can go to is here. Why? Because this actual positive, the total is 21. Based on this run, the total is 21. Now, if this number here goes up, this has to come down for the number to stay at 21. If this comes down, this must go up in order for this to stay at 21. So this is what tuning model is about. So we've built this model. Our goal now is to tune it such that the number here comes down. If this number comes down, that means the people that are actually positive, that we wrongly classified as negative, will be few. So maybe let's say we only have 1 or 2 people here that are actually positive going to have this disease down the line, but we wrongly predicted them as negative. If we have just 2 here, and this is about 19, then the model is going to be, I would say, very, very okay, because the margin of error is very low. Or better still, let's just say we have 1 here and we have 20 here. That's going to be considered a fantastic model. Does everybody understand my explanation till this point?
Yes.
Yes,
Right.
yes, I do.
All right.
Yeah.
So it's important that you understand these confusion matrix, because depending on the situation you're working on, different things will matter. Here, our focus is on this because we want to save people, right? In some situation, it can be balanced. You may want to as well. I mean, here we are assuming that since it's just lifestyle changes, even these people that are wrongly classified as going to have it, if it's just lifestyle change they have to do, and the lifestyle change is not going to threaten their health in any way, it's not going to have any adverse effect. I mean, if you are just going to say, okay, stop eating food that will lead to obesity, okay, stop eating late at night, okay, if it's just those, I mean, those are healthy things anyway. So even if this number is this high, we can still manage it. So I can say our goal is not to reduce, I mean, we need not worry much about this group of people. And as well, the predicted negatives here is naturally high. I'll explain why later. I mean, time is already fast spent. Let me just mention it. We have imbalance. I mentioned it yesterday that our data set is highly imbalanced. So what usually happens when you have an imbalanced data set? Imbalance, what I mean by that is one class of label is very large while the other one is very small. I have a chart here that I showcased. You can see these are the people that are positive and these are the people that are negative. So this imbalance usually leads to poor model performance, data imbalance. So you have to take extreme caution, extreme care to ensure that your model performance improves. Okay. So because of that imbalance, the model tends to get used to the people that don't have it. So it understands those people very well, and it's easier for it to classify somebody as not going to have it. I mean, it hasn't seen enough example of people that have it to understand their own pattern as well. So it's easier for it to guess people that don't have it correctly than people that have it. I hope this is intuitive enough for everybody. So now let's see precision. So precision, I explained this a little yesterday. So let's use this example here. Precision, I mean, positive is our target here. Positive is our positive target. Yeah. Now, how precise is this our model? It says 158 plus 15, which is 173, people are going to have this disease. How many turned out to have it? 15. So this model is not precise. That's what it means. This model is not precise because up to 178 people were predicted, but you only got 15 correctly. So it's not precise. Even though the model is accurate, remember the reason why it is so accurate is because this class level is very large. I mean, many of them were predicted correctly here. So, but it's not really our concern, and that's why our focus is not on this. So your precision is low, is an indication that your model is not so good. But we have another, okay, so this is the formula, true positives. True positives here is, you predicted positive and it turned out to be actually positive. So this is our true positive, 15. Predicted as positive and is actually positive is called true positive. Oh, I should have added it. So let me quickly add that so we can be able to relate well with it. So this is true negative. Let me write it in full. True negative, false negative, true positives. Yeah, and here, oh, this is true positives, I beg your pardon. This is false. Okay, so we said predicted as negative and is actually negative. I mean, that's true, right? Here, predicted as positive and is actually positive is also true. So you predicted positive and it turns out true. You predicted negative and it turned out true. But here you predicted positive. Oh, still wrong. So you predicted positives here, but it turned out false based on the actual. That's intuitive, right? Here you predicted negatives. I'm talking about this. You predicted these values here as negatives, but it turned out to be positive, so it's false. I hope it's intuitive for us to understand. All right, so precision here, based on this, you can follow through. We've explained what precision is, that you said 15 people are going to have it and only 150, and only, I mean, you predicted everybody here, which is 158 plus 15, that's false positive plus true positive, as going to have it, and only 15 have it, the true positives. And that's how we came about this. So recall now. So recall is basically, you want to know how saving is this model. I mean, the goal of this model is to save people, right? So how well can it save people? That's recall. So if 21 people are going to have it and it only correctly predicts 10 of them, that's less than 50%, then it's bad. So basically, in this situation, recall is our most important metric because it tells us how well can this model save the people we want to save. So it is, I think it's also called sensitivity, if I'm not mistaken. I'm not quite sure, but I think it's called sensitivity, either sensitivity or, yeah, I think sensitivity. I hope I'm correct. So How many people are going to have, oh no, I'm wrong. I just remembered. Anna, so you know the number of people that are going to have this, I mean the number of people that are going to have this in down the line, how many of them were you able to predict correctly? So that is what your recall is about. And you can see the formula. You can relate with it. So F1 score is another metric. So where there are situations whereby both of them, both these two values have equal weight. You know, like this example of more importance is our recall, like I've said. But there are times when both sides can be equally important. So if you decide to say precision alone, precision can be high while recall is low. I mean, as we saw in this example, recall is high, precision is very low, 0.9. I mean, this is 9%, or let me say 10%. It's very, very low, but it's not the important thing here. But there are times when recall can equally, precision can be equally important as recall. So in such situation, you don't want to choose one of these two. Instead, you may want to work with a balance between the two, and that's where F1 score comes. So it's 2 times the precision multiplied by the recall divided by the sum of precision and the recall scores, and that gives you your F1 score. So let me check the. So next, what can be done to improve this model? So one approach that we can use to improve the performance of this model is to change our, to make the data, we say the data is not balanced, right? So what if we try to make it more balanced? So let's see the function we have here. I'm going to copy the function and bring it down here. Although I could have done that here, I think I'll just do it here. So I'm going to add another parameter, which is class weight. And I'm going to set it as 0, 1. So this is to tell you that the two classes are balanced. Class 0 is 1, class 1 is 1. They are balanced. So use the same ratio. So I'm going to set the default. Now, in the model, in the logistic regression model, there is an argument called class weight, whose default value is none. But here I want to set it. I want to be able to set it from this function, and that's what I'm going to do here. So I just run this. It does not affect the model we have. What's okay? Data 2. Oh, data 2. Yeah. So it doesn't affect the model we have previously. But let's see. In the next example, we'll try to make use of this class weight. So train model data 2, then let's say class weight equal. So now remember, class 0 has the higher number of instances, right? So we want to balance it out by saying, okay, let's make class 0 not up to 1%. Let's make it 0.2, for instance. And class 1, let's make it 0.8 maybe. And let's train the model. Is there an improvement? Let's see. There seems to be an improvement, but our recall suffered, our precision got better, and the F1 score got better as well. But remember, this particular model we are building, recall is the most important metric for us. So if our recall has suffered here, then I'm not sure it is worth taking. So we might want to try various other things. So let's increase this to maybe 0.4 and maybe make this 0.6. Okay, our recall has gone up a little bit. Let's still do it for that. Let's make this larger now. 0.6, 0.2, 0.4. So it has also gone up, but our F1 score and precision have suffered. But like I said, the goal of this model is recall. However, I'm showing all of these just in case you're faced with other situations where maybe your F1 score is more important. So you might want to consider altering the class weight to balance it out. I think that is all we have to discuss today. And this brings us to the end of the 10 days training, 10 days, 5 weekends. So 5 weekends and 10 full days. So it has been a very long journey, and I thank every one of you for trusting me to take you through this journey. I leave room for question and answers. I'm not sure we have much time left. We have just 5 minutes left. So let's quickly ask questions. Okay, so somebody said, thank you very much, sir. I will really need to watch the video again. So it's all right. It's all right. However, if there are things I can immediately answer, you can say it out and I'll try to answer it. But while watching the video as well, if you have questions, always feel free to reach out, whether through the classroom. The classroom is going to be left up for the next 2 weeks because I'm going to post the final capstone project. So, and after 2 weeks, the class is going to be disbanded. So during that time, you can reach out through the classroom, or if you wish, you can reach out through our email to me or any of the other mentors. Any other person with any question or comment? Okay, so there seems to be none. So the Capstone project, like I mentioned yesterday, is going to cover, you're going to have to do basically all we've learned from start till this point. And in fact, if we actually look at this particular notebook, what we did between yesterday and today, it's kind of entail all we did from the start, with the exception of NumPy. We didn't have to make use of NumPy here, but NumPy is a module that you will most likely need if you'll be doing very much of machine learning. So you will be needing it. These are quite straightforward problems. We've not had to engineer some new, a lot of new columns or some very advanced engineering. So that's why we've not had to make use of NumPy. So just trying to let you know that NumPy is very, very important, irrespective of the fact that we've not had to use it here. All right, so at this juncture, we can call this class, we can bring this class to a close. So thank you all for joining. Thank you all for trusting me. And please try to complete the exercises so you can, you've joined this class so far, you've been very active till this moment. Try to complete the assignment so that you can get certificates for your efforts. All right, so thank you. Have a lovely evening. And be on the lookout for subsequent trainings I will be organizing as well.
Thank you very much.
Thank you very much, sir.
You're welcome.
Thank you.